So you know that for a vector quantity, it should follow the triangle rule of vector addition. So suppose this is vector A and say that's vector B. So you just uh, can add vector A and B like this. A plus B. So that's the resultant vector A plus B. Now also commutative law is applied for vector addition. That means if the quantity has to be a vector, then A plus B is also equal to B plus A. Now that means you can add B and A like B and A or A and B. It's same thing. So you have this. So this is the vector of this A plus B. Now let's see about rotation. Now let's see here. Say in this case, so I have drawn the x, y and z planes and there is a box, a particular orientation of the box is there, and then you rotate the box about the x-axis in this way. So this is the orientation of the box after being rotated about the x-axis, and then you rotate it about the y-axis in this following way. So due to these two rotations, this box gains this orientation. Now let's do it in case 2. So let's name it, that's case 1, and let's look at case 2. So the same configuration of the box is there. Now just you reverse this rotation order. So instead of first about x and then about y, first let us rotate about the y axis by 90 degree. So as in the previous case, just to swap this order of rotation. Now let's rotate about y axis and then rotate about x axis in the same way, just to reverse the order. Now see this orientation and this orientation, these are not same. So that means the finite rotations are not commutative, that's for sure. Commutative तो नहीं है. That means if you rotate about x then about y by, I mean here it is 90 degree angle. So first you rotate about x then about y, and then in the other case, case 2, first you rotate about y then about x, doesn't lead you to the same result. Now let us see this. So infinitesimal small angle. Now we will rotate first about, say that is a solid body, rigid body. These two cases actually. So here I'll write here, this is case 1, and just to the side it is case 2. Now in case 1, first you rotate about a small angle d theta 1 about the z axis. So about the z axis, now say this is the origin of the coordinate system O. So if you rotate about d theta 1, distance OP is r, so r d theta 1, this distance is r d theta 1, displacement of the point P to then this point, and then you rotate about d theta 2 about the y axis, so it becomes r d theta 2. So you know the resultant displacement is given by this parallelogram law. So this is say this is r, say now that is the resultant displacement, say I name it ds. Now let's look at case 2. In case 2, first just I reverse the order of rotation. So first d theta 2 about the y axis, so there it is r d theta 2, then d theta 1 about the z axis, there it is r d theta 1. Now let us look at the displacement. So this is ds. Now I put a vector sign ds. So from here you see that these are commutative. That means whether you go for case 1 and case 2, you have the same. Now, so we can represent the infinitesimal angular displacements as vectors. Now let's represent like this, d theta 1 this way and see this one d theta 2 this way. Now here also in the other case this is d theta 1 and this is d theta 2, and we can write d theta is equal to d theta 1 plus d theta 2. Now this d theta sits like this, d theta vector will be here, d theta will be here, and it will be this angle, see, yeah, d theta. So it is same in both cases, see, d theta is same in both cases. Okay, so that's why the infinitesimal angular displacements can be regarded as vectors. So as infinitesimal angular displacements are vectors, so just to insert this dt below, so angular velocity is also a vector. So let's look at this case. So now let's look at this body. So these are the two angular velocities omega 1 and omega 2 as shown in the figure, omega 1 and omega 2. So now see in this case it's actually the body is rotating about this point. See here, just to draw the vectors along the axis, the angular velocity vectors. So this will be omega 1 direction, and this direction it will be omega 2, and the resultant angular velocity is c is the vector sum of these two. So let us draw this parallelogram. By this parallelogram law, this omega is the final or the resultant angular velocity. So that means that's the vector angular velocity, but if you see the sense of the rotation, it's like this. So that's how this was a brief explanation why the finite angular displacements are not vectors while the infinitesimal angular displacements are vector, and hence the angular velocity is also a vector quantity. And I have also demonstrated how by right hand thumb rule we get into the direction of this angular velocity. And see if so again I am showing the right hand thumb rule, it's like this. So that means say any angle, if it is like this, the corresponding angular quantity is like this. So if the angle say a small angle rotated is d theta, so the corresponding vector will be following the right hand thumb rule. It holds for angular velocity and the angular acceleration as well. So as the angular velocity is a vector quantity, say this is a rigid body, and say z axis body is rotating about z axis, angular speed omega. So if omega is represent like this vector, so let's take a point here. So this point r omega. So this point, say I consider this plane actually. So that's the xy plane. Okay, this is the xy plane. So let this xy plane cut this body here. So if the body is rotating about the z axis, so the velocity of this point obviously is this way, and we know that v equal to r omega. So if you about point O, this is the position vector r, so we can represent the velocity as omega cross r. So omega cross rc, so omega is to the top and r is this way as it is shown. So omega cross r gives you the direction of the velocity.